Okay, so our basics of rotational motion. We've already talked about how a torque causes a rotation, right?
Yes.
So once something is moving in a circle, the reason that it continues to move in a circle is because there is something that is always pulling in on it. So we have what's called a centripetal acceleration, an acceleration directed toward the center that is caused by a centripetal force. So we still have F equals ma, but our F and our A's have a little c to them, and that c stands for centripetal. And centripetal, of course, is a fancy Greek word that just means center seeking. Center seeking. So they are always pushing in toward the center. So anything that moves in a circle has something that's pushing in on it. When you run around a circle, what happens to your body? You lean.
Oh, yeah.
So as you're going around, you're running straight, and then you get to the circle, and you lean. Why do you want to lean? Because you're going to fly out. It's going to be easier to keep that turning, that leaning part of your weight. Your weight is pushing in that direction, and that, as you're going around the curve, is providing that centripetal force. So the lean is providing that. If you're on a motorcycle, same thing. If you're upright, you go straight. If you lean, you turn as long as you're leaning, and then you go back upright and you go straight again. We see this in roadways. Right now they're building a bridge that's over. It's going to be the interstate down there on the loop is turning into an interstate. You've probably noticed that, right? Okay, so if you see that the bridge that they're building very, very slowly over International there, if you look at the bridge is tilted.
Yes.
And you see it tilt. It's not that severe. But anyway, you've got the little supports that are underneath it, and there's a tilt to it. And the tilt is to there. The tilt is if you're going down the loop from Mines Road toward International, the tilt is this way. And you can see it if you go underneath and you look, you're like, hey, that's really tilted. And it's tilted because right there it's starting to turn south from going east. So that tilt of the road is, again, taking your weight and providing that centripetal force to get you to turn nicely, because you'll be eventually turning down that road at a high rate of speed. So we always have that. If the F disappears, then straight line motion comes into factor, because straight line motion is natural motion. That's what you naturally want to do. So we have our little ball on a string. If we have our ball on a string, and I'm holding onto this, if I pull this really slowly, then it hangs out really low. But if I go faster and faster and faster and faster, the ball gets higher and higher and higher and higher. It also pulls harder and harder and harder on my finger. Down here, the ball was hardly pulling at all, and it doesn't pull on my finger very hard. If I get all the way up here, it's pulling really, really hard on my finger. I'll let you guys try this a little bit so you can see, you can feel the fact that goes. But again, the whole reason that the ball is moving in a circle is because I am pulling in on it, and when I stop pulling in on it, it will stop moving in a circle and goes off in a straight line. So again, the only reason you go in any circular motion is something has to be pushing in on it. So it has to. Now, if I am over the Earth, and I'm up here trying to establish a nice orbit, the only reason I can travel in a circle around the Earth is if something is pulling in on me. And so what is pulling in on me is my weight. And so my weight is what's doing the pulling in. So my weight in this case becomes the centripetal force. So my weight provides that centripetal force. And you're saying, well, but where does your weight come from in general? Your weight comes from the fact that you and the Earth are pulling on each other. So the weight is coming from that gravitational force. And of course, if we take the mass of the object that's orbiting out of the equation, then basically we just say G is providing the centripetal acceleration. Either way, you're looking at the same idea. So there are some equations that went with all of this stuff. And so I'll show you basically all the equations.
I did my homework.
You just wanted to get that on tape so that we could all know that you did at least one time. Okay, so the FC formulas are going to be mv squared over r, or m times 4 I squared r over t squared. So m, of course, is m. That's not too hard. R is radius. The v here is the speed that you're going around the circle, and the t is the time it takes to go around one time, or the period. So t is period, which would be how many seconds does it take to make a revolution. R, of course, is radius. And it's going to be that. It's going to be the speed. So those are pretty straightforward, and we can get the same equations, and if we know that F equals ma, if I take out the m's, what's left is an a formula. It would just be v squared over r, or 4 pi squared r over t squared would be the a's. I'll write that over here. So those would be the A version of the exact same formula. Now, when we are trying to establish orbit over the planet, then we're just going to figure out what the orbit velocity is by using this formula. So if we solve that formula for V, R comes up, and our AC is really being provided by gravity. So it can look like this, or it can look like that, whichever one you prefer. And the R is not going to be the radius of the planet, it's going to be the radius of orbit. So it's going to be this entire thing would be the R. Now to find those gravitational formulas, we learned that, of course, the gravitational formula is G times M1, M2 over d squared. And we said that that gravitational force was your weight, so if we take out your mass from this side and your mass from the other side, what's left is G on this side, and the mass of the Earth, or the mass of the planet, and the distance between them becomes the radius of orbit there, because we measure our distances from the center of masses. Now, since this is the G equation, then you say, hey, G shows up in the orbit velocity formula, so the other way of writing the orbit velocity formula is we can shove this G equation under the radical, but there's an R next to the G, and so that would cancel out one of the R's on the bottom, so we end up with G times ME over just one R, would be our orbit velocity formula. So either one of these works. If you already know what G is, then you'd use the top one. If you don't know what G is, you can use the bottom one. And that'll figure out how fast you need to go to establish a nice circular orbit. And again, you need to know what big G is. Big G is the universal gravitational constant, which is what number?
6
point something.
6 point something.
6.67.
You do 11th, right?
Yeah, very good. -11. And that was in newtons and meters and kilograms.
What's G prime?
So that was good. You guys remember.
Smart. What's G prime? Or is it just gravity?
G prime is the acceleration due to gravity, but it's not necessarily 9.81. That's why if you don't see the prime, you think 9.81. If you do see the prime, then you think, okay, it's something different. could be on the moon where it's 1.63, or it could be sky orbit where it's going to be smaller. So those are all of the basic formulas that you should have learned, ideally, last year. At least if you were in my class. If you weren't in my class, then I don't know what you learned.
None of this.
None of it. You probably just talked about things go in a circle and things fall.
I don't remember this.
Yeah.
I think I read it. Was there a planet lab for this?
There was. You were with Miss Vega? She likes that planet lab. I made that one up.
Nice. I actually did my homework that day.
Yeah, she likes that one because by the time you fill out that thing, you know how to plug in all the formulas. So
Yeah. And there's like 4 formulas of harmonics.
yeah. Oh, there is one other formula that I didn't mention. If you want to know what is the speed going around the circle, then if I'm going around the circle at a constant speed, v of course is equal to d over t, but the distance around the circle is its circumference, so that's going to be 2 pi r, and the time once around the circle is going to be the period, so capital T. So to find the v, we can also use 2 pi r over t. So that's pretty much every formula you'd want
How come
to deal with in circular motion.
you link the first blue formula and then the one that is G prime and R square rooted?
Because these are both finding orbit velocity.
And then the green one and the red one?
The green one is just how fast you're going when you're moving in a circle. Okay, now in today's lab we are going to get that space shuttle orbiting. And we're going to figure out a couple things. Does anybody still read this? So what's going to happen is, like I said, when I spun that ball around my head and I spun it really slowly, it hung really low, right? So the ball was hanging down like this when I was going slowly, but then it moved up, 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 closer to horizontal as I was spinning faster. Why was it hanging low in the first place? There were two forces fighting. So we have the weight of the ball, force caused by gravity. So the weight of the ball is pulling this way, and what was pulling this way?
Centripetal.
Yeah, the centripetal force. So we have the centripetal force and the weight, and those two were combined to give me the angle that we get there. Now when I spun it faster and faster and faster, what happened to the weight? Nothing happened to the weight because it was the same ball, so the weight didn't change. But when I spun faster and faster, what happened to the centripetal force? When I spin it faster, now the centripetal force gets bigger, but the weight doesn't get bigger. But you see how this is going to change the angle that it's hanging at. So first it was drooping way down here, now it's only drooping to here. As we spun it faster and faster and faster, and this got bigger and bigger and bigger, but the weight stays the same, the angle gets closer and closer to horizontal. This making sense?
Yes.
So what's happening is, if we can figure out what angle something goes at when it's in equilibrium, we can figure out what speed it's going at. Because if I know what the weight is, I can figure out the FC. From the FC, I can just use the FC equation and solve for V. But it also changes with what is the radius. So if I'm like this, I think this is the radius because that's the length of the string, but really that's the radius. Make sense? Because the FC was pulling straight this way, and so the radius is also going to be measured in the same direction. So the length of the string is not the radius. If I'm going really fast, the length of the string is very close to the radius. If I'm going really slow, the radius is very small compared to the length of the string. So what we're going to do is we're going to get the little space shuttle orbiting, and it's going to be orbiting around, making a little cone through the air, and we're going to try and measure what the angle is, and from that we're going to get all of our other stuff from it. So I've given you all the clues here. We have all the formulas. Once we get our measurements taken, we'll have it made. So the measurements that you need to know, the mass of the space shuttle is 177 grams. And the length of the string from where it pivots down to where it is 1.07 meters. And all we have to do is find the angle that it measures as it's spinning around. So that's what we'll work on next, is figuring out the angle.